So this is the first time I'm streaming on YouTube. Just gonna wait to see if everything is correct before I start doing what I'm gonna do. And it looks like it's working. Yeah, hopefully it's working. I guess I'll check it out later. I'm gonna close the window here. It's a little bit weird because I'm gonna be using YouTube as a stream on the same account. So yeah, okay, I guess it's working. So there's a lot of stuff that I have to do outside of a stream. A lot of stuff that I have to study, so I'm not gonna be here for a long time. I think I'm gonna be here for 2 hours, and I'm going to start by doing the Italian thing. Let me just close VS Code and open the Italian folder. And then after that, I'm going to train PyCharm. I think I want to spend a lot of time training PyCharm because I haven't trained in several days because there's so much stuff to study. So I kind of want to catch up, and I want to be done with the shortcuts as fast as possible, both to PyCharm and VS Code and the terminal. I think I'm on the correct. Yeah. And then after that, I think I'm going to, if there's time, I think I'm going to study how to save H5 files, which are types of files that are faster than data frames, pandas data frames. And I'm gonna do that for optimization. Because when you get large amounts of data, pandas starts being ineffective, and then this file format seems to be faster and more efficient. And I'm also going to study the libraries in Rust. And I'm probably not going to have any time after that, but then if I have time, I'm going to continue to build a poker tool that I was building. That I still haven't touched.
Io,
Io,
I,
il suo,
il suo,
his,
che,
that,
lui,
lui,
he,
era,
era,
he, she was,
per,
for,
su,
su,
on,
come,
come,
as, like,
con,
con,
with,
loro,
loro,
they,
essere,
essere,
to be,
a,
at,
uno,
uno,
one,
avere,
avere,
to have,
questo,
questo,
this,
da,
da,
from,
di,
di,
by,
caldo,
caldo,
hot,
parola,
parola,
word,
ma,
but,
cosa,
cosa,
what,
alcuni,
alcuni,
some,
è,
is,
quello,
quello,
that,
voi,
voi,
you, place,
o,
o,
or,
aveva,
aveva,
had,
il,
il,
the,
di,
di,
of,
a,
to,
e,
and,
un,
un,
a,
in,
in,
noi,
noi,
we,
lattina,
latina,
kin, of soda,
fuori,
fuori,
out,
altro,
altro,
other,
erano,
erano,
che, quale,
chi e quale,
which,
fare,
fare,
to do, make,
loro,
loro,
there,
tempo,
tempo,
time,
Se.
Se.
if,
Volontà.
Volontà.
will,
Come.
Come.
how,
Detto.
Detto.
said,
Un.
Un.
an,
Ogni.
Ogni.
each,
Dire.
Dire.
tell,
I got a contradictory translation for ogni when I looked into Google. It says that is all, and here it says that is each, so I'm not really sure. I guess it's a word that can have multiple meanings. But I hope that the stuff that I'm using is the correct translation. I'm going to start by going over the other, because I think I went over the first one a lot already. So probably I'll come back eventually to the first one. Let me open the poker file. I also forgot to let me think about where the poker stuff was. It's not in Rust. And there's so many files. Oh, it wasn't the first one. Poker hands. Also forgot to check if the name is correct for the string. So I think I'm gonna do that. Yeah, it doesn't show anything. But I guess it's fine. Yeah, it doesn't show anything. How do I change the name? Maybe I shouldn't be doing this on stream. Just so I don't leak anything. Oh, but I can change the title here. Now I think it's probably the correct name. Yeah, okay. So now let me start practicing this. I'm gonna put some music. Let's strictly bar. The tough part about this is that I don't know what the commands refer to in what exactly they do in PyCharm, and I don't feel like the problem is that some of them require you to have classes or other stuff, and I do wanna find a project that I have a class on and then do the command. The parameters. And I'm drinking tea. Shift down. Control V. Oh fuck. Control Alt too. Nice. I think I'm gonna do the VS Code one first. I'm gonna separate a time for this because I don't feel like doing this today. My mind is very occupied, and I'm not sure if that's the correct word, but there's a lot of stuff in my mind about a bunch of different things, so it's kind of hard to concentrate this. I wanna study the Rust optimization first, I think. Not first, but as fast as I can. Start doing that. I'm kind of avoiding it because it is gonna be a little bit annoying, I think, in the beginning. And that's why I think I should do it as fast as possible, just to get over that initial resistance. Yeah, I think 15 minutes is probably fine. These outs. Outs though, yeah. So is why is not working? Yeah, for some reason the out doesn't work. I think it's because of the keyboard layout, probably. Third line above. These commands are kind of useless because I'm using the Vim extension. Yeah, the keyword, the arrows don't work. Oh, now it works. So I guess it doesn't work only with the control. Elite line. The other thing that I'm thinking about, maybe I'll check if I have Vim here. I have Vim. Maybe I should download Emacs as well. The biggest problem for me with going to Vim is the file system. And understanding how to navigate files, because I don't like not having the folders here displayed. Because I like to have a general view of the project that I'm working on. And that's a very good thing about PyCharm and VS Code. Remember that this is to open a new file. How do I open this? I should have pressed U instead of Ctrl Z. If I type this... No. Yeah, that's the biggest problem. I'm gonna have to watch videos on how to navigate the file system to move on to Vim. And I'm not really sure if it's worth it. I have to think more about that, because so far I think VS Code is good, but then the problem with VS Code is that because I'm using the Vim extensions, I have should disabilitate or to remove the control shortcuts, because otherwise Ctrl C, Ctrl V doesn't work on Vim, on the Vim key bindings, on VS Code. So I guess that makes it so that I lose a lot of commands from VS Code, because I think the main command that I want to find out is how to select multiple different things in the file, which previously I used Ctrl D, I think, in VS Code, and to change all of these things at the same time, and that's a very useful thing. But now I can't do that because I'm using the Vim bindings. So that's the main motivation to go to change to Vim instead of VS Code, but I think I'll wait a little bit, probably. Maybe in 2 months or something like that, I'll change completely. Fuck. Hmm. I think you can remove the delay now. I'm thinking about, let me see. Let's see how do I cancel the subscription to make sure that I don't spend more than 2 months on this. Because they charge automatically. It looks like there is no way. Whatever. Guess I'll just ask for the refund if I forget to send them a message to not charge the next month. Oh, there is a space here to cancel. Okay. So you just go in this page and then you click view accounts, and then there's a thing there to cancel. Start line above. And this is the one that I can do. Also can do this. The shift key. I think I'm gonna stop here. I'm already tired of doing this. Yeah, so what I'm gonna do is try to append. I think I solved this stuff off stream, the remainder of this, but I pretty much put all my hand histories into the all hands tags file by creating this group files script. And yeah, the thing that I did off stream was move this stuff. This code was on main, and then I moved to this file, and then I created this other file, and then I put it here. And the reason why is because I wanted to separate everything in modules not that I want it, I have to do that. And I think that's the best practice from now that I think about it. I was studying some stuff about Python as well. In Python, you can run scripts by running the file, and it's something that I do very often because it's just easier and it's just a lot better for the way that I'm trying to, the stuff that I'm building and the stuff that I'm doing. Because I don't want to run the whole project just to see if the file that I'm working on works or not. So that's why running the file as a script is a lot better to me. It makes a lot more sense to me because I can run one file after the other and I can work on each one separately instead of having to run the whole thing just to check the file, to try to build or debug the file that I'm currently working on. Which is probably something that I have to work as well on the debugging, using more the debugging, because I never use that. I always use print statements. It's just easier, and I never felt the necessity of using the debugging. I could just do print statements and think about it, but I guess the paradigm shift that I have to make is to separate everything in modules and then run things based on the main file. But is something that I'm struggling with because it's kind of hard to search for exactly the difference, what the difference is from the way that I'm doing right now and the way that it should be done, that is recommended. Because in Python they say that is an anti-pattern to do the stuff that I'm doing, because the issue you have is with relative imports. If you do relative imports in Python, it's not going to allow you to run the file as a script because of the import module system that requires, there's something with that if name equals main. When you run the file as a script, then it's considered that should be, the name becomes main, and that changes the importation system, the way that Python views the file structure. And if you do relative imports, it doesn't work. So the solution people find is a hacky way to do it, which is to use the sys system to append the path into the file, into the Python import system, and that way you can run the file. Or they tell you to run the file with the M switch, which ignores that, or you have to run it from the initial folder. So it's kind of like the same paradigm that it is here in Rust, and it seems that this is the way that is recommended to do it, which is you have the main file, and then from this main file you run all the other modules. But yeah, the way that I currently think that people do it, but I'm not really sure, is to have the main file, have all the modules on the main file, and then just comment the modules out once you want to test one. So for example, here I'm testing the file, read file. If I want to test it, if I wanted to test the group files, what I would do is import as a module here, and then I put it down this line, group files, etc., and do the same thing that I'm doing here, and then comment this one out, and then run the main file, and then it's only gonna run the group files. So the main works kind of like a routing path for all the other modules, and that's the better way to structure things, instead of running each file on the specific local, instead of running like this and then running the file, which you can do in Python but you can't do in Rust. You should put everything on the main and then comment out the things that you're not going to use, and only run the things that you're testing for. Yeah, so what I did here is separate this into two modules, and then I created this to append all the hand histories that I have into the all hands text. And then I wasn't being able to read this manually because the file is too big, so I created this thing here to read the file. And I think, yeah, this is gonna read the file probably, unless that breaks something. I mean, the last time I remember working. And the file contains all the hand histories that I have. So what I'm gonna do, I think, is, well, maybe I should try to see if I can save it in HF format. But I was thinking about doing is reading this text file and searching for patterns. First, I have to separate I have to read the format and understand what each thing is. Then I'm gonna think about what is important to me that I wanna analyze. And then I'm gonna create a bunch of different regex patterns to filter this text file based on that. And I'm gonna append this information into either, it's probably gonna be HF because I wanna train HF, but it's too hard. If it's too hard, I'm gonna do it with CSV first. But I think, yeah, I'm gonna force myself to do it with HF to understand how HF works and how to work with HF in Rust. Then after that, I can use that information to make conclusions about my play and then try to connect this with BioSolver, which is a solver for poker that everyone uses. And what I'm gonna try to do is try to create simulations on PyCharm that exploit my play, or that exploit my opponent's plays, and maximizes against, creates an exploitative strategy against them. And I'm gonna compare that with mine and see, and try to draw statistics about what positions I'm worst at, and try to improve based on that. But obviously I'm not that concerned with that. The only reason why I'm doing this project is, not the only reason, but one of the reasons is, the main reason I would say, is to improve on Rust and yeah, understand these things so I can use on the other projects. Understand how to deal with large files in Rust and how to optimize the data frames. I want to understand if I can save things into columns. I think I can because from the stuff that I've seen on Python is similar to CSV. Or people use it in the same way. I'm not sure if it's similar. The fuck? I think the easiest way is probably search for videos in the beginning. The easier superficial topics is better to search for videos, and then as I get into depth, it's better to search for articles and text. And I think this is one of the things that makes Rust more difficult than Python, is that you have less people, so the community is smaller, so there's less information about it, about how to solve problems. This is the one that I saw, that is supposedly, according to these people, the guy that made it, it's a lot faster than than pandas than CSV. Oh, H5. CSV, H5. Oops. I want to understand how I'm supposed to write information to the file. If it is in the same way that a CSV works by writing each column, or is it different?
This course, we explore a technology called HDF5 and see how to use it from within Python. HDF5 lets you organize, access, and share large amounts of information, along with the context that makes it useful. Although HDF stands for hierarchical data format, as you'll see, HDF5 is much more than a simple file format. It's a powerful way of organizing information, an extensive but easy to use programming API, and a rock-solid, high-performance software library maintained by a dedicated nonprofit organization. Over the past several years, HDF5 has become a commonly used technology in the Python and NumPy communities for handling large numerical data sets in an organized way. To get started, let's discuss the kind of problems that HDF5 is designed to solve. Real-world problems come in lots of different shapes and sizes, but many share one common theme: they need to manage a diverse collection of data objects. Not only can a scientist or developer become overwhelmed by the sheer quantity of information, but it can be hard to figure out how to organize the information in a way that can be easily understood, maintained, and shared. Other common themes apply to any technology used for managing data. For example, it's highly desirable that a solution be high performance. In other words, that it support reading and writing data quickly. Another is the ability to scale to large data sizes, much larger than will fit in memory, and sometimes larger than will fit on a single computer. Likewise, any solution should be flexible enough to handle many different kinds of information and relationships between data elements. In other words, it should support heterogeneous data and diverse organizational structures. HDF5 addresses these areas in different ways. To get started, let's talk about one of the most common challenges in data management: handling many pieces of information of different types. Let's suppose we wanted to record the results of an experiment. In this example, we're developing a new kind of machine, performing field tests for a new kind of aircraft engine. The results of the test don't arrive together in a bundle. Instead, we have a set of data from the engine, aircraft electronics, another containing sound and voice communication over the radio, another with GPS information as a function of time, yet another with video and image information on the ground, along with other records, radar data, and so on. How should this information be represented? And more importantly, how can we organize it in a way that lets us draw conclusions about the test? Let's see what happens when we try to record this information using common methods based on the file system. First, we'll have a written log, maybe a text file, containing notes about the test. Then, we'll have an image series, which tracks the aircraft as it goes through the trials. We'll also have sound and voice recordings, then raw data on aircraft performance, some additional sensor readings from various equipment on board. We also have a video series recorded by an onboard camera, and later tests, more camera angles, and more, and more. And finally, we have the results of our test as a big pile of disconnected pieces of data, all stored separately in their own formats and with their own metadata. This is how it might look on a computer. The data consists of a number of files. How do we keep these files organized? You might notice one common approach seen here: we put the information in the file name. That's because, apart from format-specific information like image size and color depth, the only place we can add context information is by editing the file names. We might introduce a naming convention, reserving sections of the file name for things like the date, the trial number, or an inch count, for example, 001, 002, and so on. Or we might decide to create a directory structure that captures some of this information. But that creates another problem. Since each file can only go in one folder, we have to decide ahead of time how to organize the data. So, for example, we might have a folder containing all data records for a particular flight. This works well if we want to retrieve all data on a per flight basis. But what happens if we want to read just one piece of data, for example, engine performance, across all flights? Or, for testing, more than one prototype? With this kind of system, just figuring out how to extract the data we want can become a time-consuming and error-prone step in the analysis workflow. It's also fragile and flexible. We can restrict moving around, for example, once we start writing scripts that assume particular files are in particular locations. These problems can certainly be solved, but it's a lot of work. Of course, we can manually synchronize all this information with notes in the experiment log. The image files, for example, only carry information about their shape and color space, and it would be useful to also know what part of the aircraft to track. HDF5 is designed to address these issues. As we'll see in later lectures, HDF5 provides the means to not only store this information efficiently, but also keep track of context information, or metadata, required to make sense of it. HDF5's metadata system allows you to store information right next to the data it describes. So there's no extra step required to give your data context. All the information is in one place. HDF5's grouping mechanism is much more expressive than folders and file names. It doesn't restrict you to an inflexible, one-size-fits-all tree of folders. Objects can be found in more than one group, which allows you to create multiple views from the same data and access it in multiple ways, whichever is best for your application. And you can also create new views in your data long after data has been collected, without ensuring the structure is already in place. Using HDF5, all this information can be stored, organized, retrieved, and later updated, all in a single bundle. Here, the HDF5 file contains complete representation of the experiment. This experiment can be analyzed, shared, or archived, all in one comprehensive and self-contained piece. Let's talk about another important area that HDF5 addresses: we need to handle large data sets with good performance. For small problems, people often start off using text formats like CSV. They work quite well when data is on the order of kilobytes or megabytes. But at a certain point, the demands on disk space and memory become so large that the analysis process slows down. We find ourselves waiting longer and longer for what should be simple operations to complete. For example, just opening a data file. From the perspective of a user or developer, this is frustrating because many tasks deal only with a fraction of the data. For example, you might want to analyze only a few rows from a spreadsheet. You have a large file on disk and a smaller amount of computer memory available for analysis. This would be great if there was some way to read just the rows we want. They might fit in memory, and we could proceed. But more typically, workflows are designed around the assumption that we can safely load all data in memory at once, and at a certain point, it stops working. HDF5 addresses this problem by supporting partial I/O. In other words, the ability to specify just a portion of the data to read or write between disk and memory. From a Python developer's perspective, this means you can entirely skip the process of writing data importer. As we'll see later, HDF5 datasets can be treated much like ordinary NumPy arrays that happen to be stored on disk. That means no writing parsing or reading code. Just open the file and retrieve the parts that you want. HDF5 is an excellent platform for sharing data. It's implemented by a high-performance, widely used open source library. That means that your HDF5 files will work in Python, MATLAB, IDL, or any other platform that uses this library. It's very common in the scientific and engineering communities to use HDF5 for data interchange and also for archival use. Finally, it's important to note that HDF5 is supported by an independent, non-profit organization called the HDF Group. The HDF Group not only maintains and improves the library, but provides many useful tools and serves as a hub of the HDF community. As you consider if HDF5 is right for you, keep in mind the data management landscape and where HDF5 excels. In this course, you'll learn how to use the tools HDF5 provides within Python to develop solutions to a variety of common data management problems. We begin with an introduction to HDF5's extremely simple, yet powerful and flexible data model, organized around three basic building blocks: datasets, attributes, and groups. Next, you'll learn about some of HDF5's most powerful features, including partial I/O for fast data access, the self-documenting features of HDF5 files that help with maintenance and sharing, and compound data types that provide great flexibility in ways to store data. Finally, we'll dive into some of the more advanced aspects of HDF5 that support efficient and scalable computing, including storage layouts and compression. And we finish with an overview of some handy command line tools to make working with HDF5 files even easier. Along with the video lectures, be sure to take time to complete the exercises. After all, the best way to learn programming concepts is by sitting down and actually doing some programming.
Yeah, I didn't learn much. As I watch these videos about the polars library and see how it works, and then I'll try to reverse engineer the H5 thing from this, because there's probably gonna be some stuff on the polars, obviously, that handles different files formats. So I'm gonna understand how Rust operates with different file formats, and then that might give me a glimpse of how to deal with H file formats.
Hi, welcome to the station. I'm going to talk about polars. Polars is a new data frame library with an API for really fast analytics. My name is Richie Vink. I'm the author of polars. I have background in machine learning and software development, and I am part-time sponsored by Sony, the company I work for, which sponsors a large chunk of my time to develop polars. So today I want to talk about these topics. One, why polars. Two, about foundations we built on with polars. Three, about polars performance, which is really good. About one of our key selling points, which is the expression API. I want to finish off with a small example. I want to talk a bit first about bipolars, and then I want to do that by looking at current data frame implementations in Python. It's Python-oriented, but the same may apply to other languages as well. One of the problems is that approximately 50 years of relational database design and research is not really applied in the data science community, as in not in the single machine tools. It is in big data tools because there you have to, but on the single machine tools, it's not really the case. That means we have eager evaluation. Almost all implementations are eager, and because of this, we don't have any query optimization. As a result of that, we have very large unneeded materializations of memory, which become really expensive once you go to reasonable data size. The responsibility on writing fast, memory-efficient code is laid to is put on the user more, and most users are domain experts, so not really data analysis experts, and not query optimization experts. And they have a terrible memory representation of string data, which equals to terrible performance. And how did we got here? We got here because we finished with something that was already there, which was really good in what it did, which was NumPy. NumPy is really good in numerical compute, but it's not intended and not therefore also not really good at relational compute. For instance, there's no missing data. As a solution, pandas use floating point, not a number for this, which is ambiguous at least. Not a number can mean the floating point, not a number. It can also mean the data is missing and you don't really know which one of it is. And it can also lead to strange costs of column types. For instance, if you start with an integer column and some operation results in that integer column having missing values, it may be costed to floating point column to add the not a number types in there. There's no string data, and as a solution, they use box Python strings, which, if you want to reverse it away, is effectively pointer chasing. I will come to that in the next slide. There's eager evaluation, so that means there are no holistic query optimizations, and therefore there are huge intermediate materializations. For instance, Python strings in memory. So here we have a NumPy string, and if you put Python box strings in there, we have a pointer to the actual heap allocation. And if you traverse this memory, you're simply traversing the pointers following the pointers, which will be a cache miss on every string read. Also means that you'll have a lot of heap fragmentation, and you'll have quite some byte overhead string value, which will also lead to some memory overhead. And in Arrow, those strings are tightly packed. So we have a data buffer with all those strings concatenated. We have an offset buffer, which tells us where the string starts and where it ends. And we have a litigates buffers. And this is a bit packed buffer, which tells us if a element is valid or an element should be read as missing, null. There's another problem with current data frame implementation, and that's that Moore's law is ending. That means that single-threaded code is not really getting faster anymore, especially not 2 times faster anymore in the next few years. So as a solution, a lot of laptops, machines now have multiple cores. My laptop has 12 virtual cores, and if you go to the cloud, it can go to very large numbers. But at least I think almost everybody's laptop has at least 8 cores or something. And in my case, that means that if you run pandas, you run 1/12 of its capacity, of your CPU capacity, which is wasteful to say the least. Well, problems try to solve that by parallelizing pandas, but then you still simply throw more CPU power to the problem. It's not very simple. I don't think it's simple to build a parallelized pandas, so don't get me wrong. I just think that we can gain much more by rethinking the root problem. And if we simply parallelize pandas, we inherit all the problems. We still get a bad memory representation. We will still have high memory usage, and we cannot really control memory. That was already hard when you go to memory by NumPy, but the higher you go into abstraction, the less control you have. And that's where polars comes in. Polars wants to be a data frame backend query engine that doesn't have these problems and is really built from ground up to be very efficient for in-memory queries and be very smart in how it does parallelism. So polars has got a front end, and the front end is available in Python, Rust, and Node. It's an abstraction of arrow memory. I will get to what arrow memory is in a bit. It's got a vectorized parallel query engine, and it's got query planning. So query planning optimization, this means that we can often choose to do much less work than needed. It's got a very powerful expression API. It's got copy and write semantics, but then actually a little bit better even, so that's why plus plus. And we got very fast native I/O readers and writers. So one of the foundations is the arrow columnar memory standard. And this is the future in large data computations. Maybe already is. It's a standardized way of dealing with in-memory columnar data. It's also a specification of how we can share this data over the wire. And this leads to a very huge decrease in serverization and deserialization costs, especially in distributed compute like Spark, for instance, where you need the data from one representation to another representation over the wire. You can have a lot of compute just needed to transform this data. And within the same process, because all these tools understand the same arrow memory format, we can actually have zero copy interoperability. So for instance, polars can have zero copy interop with PyArrow, with trade datasets, with DuckDB, with Dremio, and likely a lot more tools. We use Arrow 2, which is a native Rust implementation. And because it's a native implementation, we can choose to use Arrow where we need it. But if you think we can do something different or better or smarter, which doesn't fit the Arrow project per se, we can still get a hold of the memory and do the things the way we like it. For instance, we use this a lot to prevent virtual function overhead. Another foundation is Rust. Rust is a programming language that's really fast. It's as fast as C and C++, but different from C and C++. It's got really strong memory guarantees, and it has those thanks to the borrow checker ownership model. I'm not going to explain it, but it makes it a lot harder to get double frees, get memory access you're not allowed to. So you have very strong memory safety guarantees, but if you don't lose control, you can still fully control memory. Make sure you traverse memory in a cache efficient way. And the same ownership model also leads to further security concurrency. It's way harder to get data races, aliasing, etc. Thanks to borrow checker. An example of something we get thanks to borrow checker is copy on write semantics, but then sort of special. So our memory buffers are atomically reference counted. That means that if you make a copy, we increment the reference count. And if the reference count goes to 0, we deallocate the memory. But the Rust borrow checker also guarantees that there are no mutable aliases. It means that when I have only a piece of memory, or when I have a mutable access to that piece of memory, no other thread, no one else is able to write or read that memory. And that means that if we combine that knowledge with the reference count, and the reference count is equal to 1, then we know that nobody else can increase the reference count, then we're able to mutate that memory buffer. So this means we have end-free data sharing, free cloning, almost free, and we have mutable access when the reference count is 1 without a mutex. So that's something that's unique about Rust ownership, which we use in Polars and Arrow too. So in this part of the presentation, we will talk about Polars performance. Polars is really fast, and it thanks this to really taking performance in mind. It's not only about parallelism. With only parallelism, you won't get as fast. We get this by having one fast cache-friendly data structures in Arrow, but also very data structure aware algorithm, cache efficient algorithm. So really, per algorithm, we think about how we can traverse our data as cache efficient as possible. We use work parallelism with a tool called Rayon, and we have a lot of in-out parallelism. We have different parallelism. That's what I want to say. We have parallelism query engine, which follows a certain set of rules, which is predictable, but we have also parallelism per algorithm, which is less predictable because it depends per algorithm. For instance, in group by, we have a radius group by, partition group by, which group by we choose for depends on cardinality of the data. We will sample it just before we do the group by, and then we will make a decision. For instance, in a radius group by, we will see how we can split up the partition, split up the units of work best for that group by operation. And the same for join operation and for partition group by operation. So per nodes per operation per algorithm, we will think, okay, how can we split this work up best? And we also have SIMD operations. SIMD stands for single instruction multiple data. That means that if you do, for instance, an arithmetic of floating point numbers, and to do a plus to compute something on floating point takes that amount of CPU takes. In the same amount, approximately the same amount, you do it not on a single floating point number, but on a vector of them. For instance, on 16 floating point numbers.
It's probably expensive as well.
This sort of inner thread, you have vector lengths, which is sort of parallelization of that work on a hardware level. And with query optimizations, because often the best work is no work. So if you can prove you don't have to do something, or you can do something smarter, go for it. And we have native I/O, which means we often can really read and write most efficient without any extra copies, because we really know where our data is, how it should be. We directly write to the data in the most efficient way. And this differs, for instance, if we have pandas and you want to read a file, and you use PyCharm, first PyCharm reads the file into Arrow memory, and then needs to copy the data into pandas itself. So you always have a double copy here. And here we see results of H2OAI's database benchmark. H2OAI has done several benchmarks with different tools, also not these tools. So Polars is in there, for instance, data table, our data table, which is a really fast data frame implementation. The ClickHouse, which is vectorized database. Spark is in there, Spark on a single machine with in-memory data. So all these tools don't operate on disk, they operate in memory. Julia data frames is in there, DOS, Modin, dplyr. So there are quite some data frame implementations, also databases, QDF. And here we see results from the there are different questions. So we have different questions for goodbye, which are start with easy questions, and then more advanced questions to really show that to increase the complexity. And here we see summarizations of those results. And we see that by summary, by every bit of the result.
And this is Python.
It's twice as fast as the next in line with join operations, and in goodbye operations, it also does really well. And besides the sheer execution speed, Polars is also very memory efficient. So here we see zoom in on the goodbye operations. And we see here the data size ranging from 500 megabytes to 50 gigabytes.
Maybe.
And 50 gigabytes data only
No, it
and
is.
Polars were able to finish without memory. But Bodin needed 128 cores to be as efficient as Polars is on 60 cores. And Bodin, if I recall correctly, does JIT optimization and scaling of pandas, whereas Polars is just written from scratch to be efficient. And really, this shows that you can get a lot with less. This part is talking about Polars expression. Polars is one of these Polars expressions are one of the endpoints of our API. And that is because we really strive for a small API service. We want to provide the user with composable blocks which are really powerful, allow you to control what you want to do, but still have performance. So in my experience, often the case was in, for instance, pandas, people wanted to do something slightly more complicated. They were needing lambdas. And once you start using Python lambdas, you're running Python bytecode, you're killing parallelization, you have to double interpret block. This is a no-go for Polars. We want to prevent this as much as possible. So we want to give you the API that should be able to express what you want. And this is similar to the vocabulary of programming language. Vocabulary of programming language doesn't have to be big. It's actually quite small, but still very powerful because of the combinatorial explosion. You can express anything you want. And expressions Polars are the same. So an expression is a type where you have a function that takes input a series and produces a series. And because the input and the output are the same, this means you can compose them. You can compose them indefinitely. And this is powerful because this is really, you can combine them as you want. And the series as input can represent different semantical things. They can be a column in a data frame, they can be a group in a goodbye operation, they can be elements in a list, and they will likely be more semantical things in the future. These are the ones we currently have. And this is a slide where I want to show this.
So it's probably the same way. I create series and then I upload the series to the data frame in the same way that pandas, which each column in pandas is a series. And then the rows are obviously the collection of columns on the horizontal line.
So here we take a column foo and we sort that column by another column bar, and then we divide it by the sum of the column hen, yet another column, but only where the column hen is equal, where it's larger than 19, where the column span is larger than 19. So this already takes 4 columns, some predicates, some sorting, division, and you don't need any. So it is very flexible. This will be ran by Polars on query engine, and we will make sure that we run this as fast as possible. But the expressions are lazy. That means they don't run by themselves. No, they need a context to run. And the context deals with expression execution. So for instance, the context can be a select statement, can be a goodbye operation, can be traversing the elements in a list. But the context depends how we execute it. But the meaning is mostly the same. For instance, here we have select context, where we select columns from the data frame, and within select context, every expression is embarrassingly parallel. So here we take a column foo and compute the rank. Here we have a when.
Well, but that's the thing. He's talking about the data frames, so it might be different if I have an HF file. I forgot that this is for data frames as well and CSVs.
Else expression, and then we have a predicate, then we have an answer when the predicate is true, and otherwise we will take the column hen when the predicate is false. This expression will run also in parallel, and we have another expression which computes the difference, which will also run in parallel. All these expressions don't need any communication, so they can run in parallel. But there's also within an expression it can also be parallelism. For instance, the when then otherwise has got 3 branches, so we can compute those branches in parallel. And branch can also be really expensive, so it can really pay off to do this parallel. The context can also cache immediate results when it thinks it needs to. For some more expensive expressions, such as window expressions, we do this. And I want to go to an example. So here I have a notebook open. I want to go to an example of how we would use pointers and the expression API. So let's start simple with a data frame. So here we create a data frame with some distributions, just sampled from a NumPy, from the NumPy random function. Voila. So as you can see, we have distribution 0 up to distribution 7 with some sample data. And let's use the expressions to play with them. So I can select, this is not a really useful example, but I can select all the columns by saying select PL dot all. Now I want to make it a little bit more useful. I want to add a column with the groups A and B depending on type. So let's type that, say PL.when, which should add an expression with condition. So when the column distribution 0 is smaller than 0.15, then I want the string value A, otherwise I want the string value B. I want to call this column groups. Voila. And I need to add a comma at the end. And when we do that, we will see we have this column groups and we have it as the first column. Because the order of selection matters. So we first select this column groups with the when then otherwise expression, and then we select the rest of the columns. Note that all the columns are, if we would select this from another data frame, we would just copy these columns without by implementing a reference count. So it won't cost you any extra data. Let's now make a utility variable selection which selects all the columns except the groups. So we want everything except the groups. So we only want the distributions. And then we want to compute the sum of these selection. So this would compute the sum. But if we want to add another aggregate, for instance, for the distribution, and we would run this, we would get an error saying that we have duplicate columns. So we can add a suffix, but we still want to keep the dist 0, the dist I name, and we add a suffix sum and a suffix entry. And now if we run this, it all runs fine and it computes those. Note that this is all executed embarrassing parallel. So you just throw something on the Euler's query engine and we will parallelize it for you. This, as you see, it's really easy to parallelize overall columns. We can also complicate these expressions. So let's say our business domain says we need to compute the sum of the selection. The entry, when the sum is bigger than 1, we want the entropy. Otherwise, we want some other complicated expression. We want to compute the skew times the entropy times 10. Some weird business logic. Expressing this is very easy with the when then otherwise expression, and we can run this and execute. But the same logic the same expression can also be ran over groups in a group by expression. So the same expression can be executed over groups, and it's not a problem. Same knowledge of Euler's expressions that helps you select things from columns applies to group by operations. So it's really easy to make really complicated aggregations. Note that this aggregation also is parallel over the. So let's compute the first of every column and add a suffix. This is also parallel over all aggregations. Voila. So also parallelizing group by context. So group by already does a lot of parallelization when determining the groups, maybe in partitioning, but also in evaluating the expressions themselves, we can compute this in parallel. And this is an example of how we can use the same logic to apply things horizontally. So let's build up. So we say we have select, and we have our selection, which was all the columns distribution 0 to distribution 7. But now we want to compute something horizontally. So we can do that by concatenating all these columns in a list. Concat list selection. This would give us a list of all these distribution columns. And a list has got quite some strong guarantees. A list is homogeneous. That means that computing something horizontally like a sum on a list of floating points is valid. If we have a data frame can have strings, can have floating point numbers, can have dates, etc. It's not really even from the type data frame how we can sum this. That's why Euler doesn't like a data frame.sum x's, etc. X is 0, because it's not really explicit that this will succeed. So if we have a list, we can take the R namespace and then eval from evaluate expression, and in here we can take any expression. So we can take the same when then expression, but then we compute it over the elements. When the element is the sum of the element is larger than 1, then we want the element's entropy. And otherwise, let's take the first element a bit shorter. Otherwise, we want to have the first. And then we see we get the aggregation but still a list. So let's say we don't want a list, we want a column, we can just press the list. And voila, we have the result of a complicated expression. Note that we're using the eager API here, but Euler actually has 2 APIs. The eager API is very similar to the lazy API, only it doesn't do any translation. So it's always better to use the lazy API, which you can just switch between by just adding a lazy at the front and collect at the end. And we have the lazy API. And the lazy API is with collect is very similar to Spark. Something you have computation more often. We delay execution until you request this execution. So let's continue with a more straining example. Here we have here we have a CSV from the yellow data set. It's a CSV with text feature data. It contains approximately 50 million rows and 18 columns, also with dates. So we want to scan the CSV. A scan CSV means we want to start computation graph. We don't want to execute to running it immediately. And what we get is an if query plan. So an if query plan tells you what Euler wants to do, but it hasn't been optimized yet. So here we see we want to scan all columns, all the 18 columns, and we don't apply any filters. It's scannable. Then we will do a filter. So we filter any trip duration that's longer than 4 minutes, and we filter any unit of distance that's larger than 1. It's just something arbitrary. And then we have an if query plan with those 2 filters. Those are not really optimal because those filters should be combined. That would be better because then we only would have 1 materialization instead of 2 because it's pretty expensive to materialize those immediate data frames. And maybe even better, we're doing scan at CSV. We'd be doing the filter at scan level, so you don't get to materialize it at all. And then we want to do a group by vendor ID and payment type, and we compute some statistics. So here we compute the mean trip duration per vendor, and here we compute the maximum number of passengers on the 31st of January. So we have a condition where the drop-off date time is between 31st of January and the 1st of February, and then we compute the max of that and call it the maximum passenger count of that day. And if we request show graph, then we will get the optimized query plan. And in the optimized query plan, we see that we do the aggregation with aggregation node, and we have scan node. And scan node only scans 6 of 18 columns, and thus filtering already at the scan level. That means we need to materialize far less rows than needed, also far less columns than needed. And if we run this, so we can run this, and I do want to run this, but I also want to show memory usage while running this. So let's move myself here. So here we see my threads, my thread counts, and here we see my memory. And if we run this, we just call collect, and polars is done in 2 seconds. And as you can see, we have a bump, and all threads were fully utilized. So this is great. We really don't see all the threads used, and we see a small memory bump. So that means we can, that's likely because we were able to do a lot of those filters at scan level. If we run the same query without optimization, then we don't do this filters at scan level, and we naively select all columns. Then polars would be still pretty fast, but it would be a lot slower. It would also consume a lot more memory. So we see memory consumption is quite a bit more. But let's compare this with pandas. So here we have a pandas query. Actually, we have 2 queries. We have an optimized query, where we are a bit smarter and tell pandas which columns we want to read, and we have an optimized query. I'm not going to run the not optimized query here because it will go out of memory. That shows how much memory pandas is using. We will run the optimized query, and this will probably take around 40 seconds. And yeah, as you can see, if we look at the thread utilization, it's very minimum. It's 1 thread that's swapping every time, and I don't think this 1 thread is fully utilized even. So it seems that there's quite some system call overhead, and we see slowly increasing memory. I want to talk about moding, which is pandas array, which really does a good job in scaling pandas and can really improve parallelization. So yeah, as we've seen, the pandas query took 37 seconds, almost 40. So I think polars was 19 times faster here and used a lot less memory. But you could also, for instance, scale pandas with moding, which is pandas array, and let's run optimized query, otherwise we will likely go out of memory. And polars does a good job. Sorry, moding does a good job in utilizing all the cores, but it uses a lot of memory because of the not so good memory representation of pandas. And we have a roll time of 21 seconds.
It doesn't work with CSVs.
So even with full parallelization, it really shows that thinking of how you should design your algorithms from the ground up does a lot. I mean, 10 times is a lot. And that also was shown in the Bolio.ai versus polars benchmark. So that wraps up my my example. Let's go to that. I want to thank you for watching this presentation. And if you are interested in the project, please go to our GitHub or go to our Discord and send some questions. Yeah, and have fun with the other presentations.
Hey guys, welcome back. In this video, we're going to be learning how we can read data from HDF5 files. In the last video, we saw how to create one. Here, we're going to read the data from the same one we created last time. So let's import NumPy as NP as usual and import this beautiful package called h5py. Let's do that, Shift Tab. And then now, instead of writing to the file, we're going to read the same file we created last time. So with h5py.file, we pass the file name as a string, the full path, and then R for reading mode as HDF. So we're going to be dealing with this HDF object, which refers to or points to the HDF5 file. And if you remember when we created the file, we gave this dataset's name. So it was a name and then data. That name, as we mentioned, it is a key. So it's a key value pair as we explained in the very first video when we had the overview of HDF5 format. So to be able to display those keys, we're going to be using this keys function. So hdf.keys, this file, hdf5 file object, .keys, it returns all the keys that it has, and what we're doing here, we're just transforming it into a list. Okay, so we save it in ls, and then we just print ls, so we'll print the keys here so we can see them, and after seeing the keys, now we can access the values by doing a get. So we use the get method, or the get function, and we give it the key name, and it will return the value. Okay, so what we're doing here is, if I comment this out, and just leave the code to print the key that we have, so we have the key called dataset1 and dataset2. Okay, and now to get the data that is with or corresponds, or the value of the key dataset1, I just say data equals hdf.get, and then dataset1, that's the key name. I run that and save into data. And now because my data is a NumPy array, then I need to transform it back into a NumPy array by doing np.array of that data, and then I should be able to get the exact data of set 1 that we saved last time. So if I have a look at dataset 1, then I should have the same values that we saved in the last video. And then just maybe to read maybe the shape of it, so it should be different, right? That we said.
So it's pretty much key value pairs.
All right. H5py is a Python library that provides a really elegant and simple interface to the HDF5 file format. It's basically a high-level wrapper of HDF5 for Python. Now, Python doesn't have an official library API to HDF5. It's not one of the languages that HDF5 supports. It supports C, C++, and Java officially. But the maintainers of HDF5 have done a very good job in creating a library that takes the concepts of HDF5 and makes them very accessible in Python syntax, and actually makes them look like NumPy arrays, which is a really accessible way to think about multidimensional data. So that's the underlying representation. If you know how to work with NumPy and access NumPy slices, then you pretty much can work with HDF5 with HDF5. It's a pretty simple framework. Here's the few lines of code that take you through how to create a dataset in HDF5. It's pretty straightforward. This is, just importing NumPy, because you actually need NumPy to declare datasets. Well, easily at least. This is the call to import h5py, and this line here creates a new h5py file. It's called, in this case, new file.h5. That little W flag means that you are writing this dataset from scratch and opening it for write mode. If there was another file named new file.h5 in that same directory that you're opening up and saving to, it will overwrite the file and delete it. So these flags matter. And if you want to not overwrite the file, append to it, then you open it in different mode. If you're reading from it, you can pass R instead of W, that kind of thing. The next step here is to create an h5 file. You get this creating a group attached to object is being created dataset against. And apologies for that. And we're making a chunk. Now that returns. I'm just indexing into the compressed CLR set h5py standard key-based indexing into that h5.
Hey guys, let's begin coding by creating a HDF5 file. We'd like to import NumPy as NP the way we do it, and then we import this package h5py, which comes by default with the anaconda distribution. Remember, we're using Python 3.5 anaconda distribution, so this package comes by default, which is very convenient. So let's import these packages, and then here, let's create whether to read or write. So W that in the video. Okay, and then now using this tool, the data is matrix that HDF terminal, so I can that's so quite nice and easy. Remember, we import stuff with pandas. Okay, so pandas is the framework. Okay, so
right, welcome to Call the Doctor. Who do we have here today?
Oops, I see Karam is still connecting the audio. So John is substituting for Garrett, and I just said we keep it informal. So feel free to unmute and talk to John and ask questions. And I'm not sure if he has a presentation or not, but anyway, let's go for it. Thanks, everyone.
Okay, so I see Marta, Karam, and Robert connecting. Welcome, guys. Yes, I'm here. Thank you. Yes, this is. Okay, great. Yeah, so I want to talk about the questions you raised. But first, let me ask anyone else has burning questions they'd like to discuss. Is that Robert or Marta? Do you have any questions?
Not today. Thank you.
Right.
No, John, I'm ready to get started.
Okay,
Thank you.
So let's dive into it. I thought Karam's question was really interesting. You guys see my screen share?
Maybe this one is
Yes.
interesting. Should say.
So a couple weeks ago, Karam was asking a question. I have a large data set, 25 million rows and 1,000 columns, and he wants to access it basically reading 5,000 arbitrary rows. He tried this with the HF5 library, and the performance was not what he's hoping for, but 90 to 100 seconds. Karam, do you want to kind of provide some background on how this came about?
Yes, okay, I'll try. Just make it clear. I'm for first time at such a conference. I work with seismic exploration, and usually we have to work with big data. Big data in the sense of maybe case like that. We have a file of size probably 100 gigabytes, and it can be represented as a cube. And we have to allow the client or the person who uses the interface of the application to fast enough switch one slice to another from this cube. I mean, we should allow him to slice our cube in first direction, in second direction, and in the third direction, in three direction. And the first direction, I mean, we are cutting the cube at the constant row, and it cuts through all the columns and all the sheets. And at the same, the second case is when we cut our cube at a constant column in a similar way, and the third case is when we cut our cube at constant sheet, constant sheet. The performance, I started my testing with a 2D dataset with 25 million rows and 1,000 of columns. It's about 100 gigabytes. The chunk size I chose for my first case is 1 by 1,000 columns. I thought that this would be probably the fastest way of retrieving arbitrary errors.
Let me see something here. Yeah, the problem is that I'm not specifying any extension, I think. Oh, here. Let's see if I just change to H5, if it's gonna work or not. Probably not, because that's the thing that I'm not sure about. Because here I'm writing the string into the file. And then, but I think the H5 format's different. It works more like a data frame, so keys and value pairs. And that's the reason why it's better to translate from the text file, from the final text file into the H5 after parse into columns. But I think it's probably not going to be different than writing and reading through any other file. It's just the format that you pass is different. So instead of passing a string, I will pass a vector. Or I think Rust has hash maps, so I'll probably pass a hash map. But maybe, yeah, this is probably gonna have be problems with that as well. Because I remember when I was doing this, I found some problems with the types and stuff like that, which I'm not very used to dealing with because I'm very new to Rust and to using types in general. The other thing is, yeah, I think you put the modules in the library and then you can access them. And you have to make the function public. Let's see if that works. Join files. I think your comment is like this. It looks like it's working. Yeah, all hands that H5. Interesting. Yeah, but I wonder, because I'm not gonna be able to. I guess I can run this script then and change to H5 as well and see if it works. Yeah, here I remember I was trying to loop through the characters to append to the reader, but it wasn't working because it says that I can't iterate over characters. And then the answer that I found was to put chars here, but it didn't work as well, so I decided to do like this, which was another solution that I found. Yeah, so it looks like it works. H5, H5. Now let's see if reading the file works. Ah, interesting. It works as well. So I think I'm gonna do it like this because it's probably faster with H5. And I guess I can write it in any way that I want, but obviously for analyzing it's probably gonna be better to write it in a CSV way, so with the columns. But then I wonder if I can use the polars library. Probably not, because like I said on the repository, you can't use CSVs with Rust on polars. But it looks like it reads a lot faster. And it probably does, so. Now I have to think about if I'm gonna use, yeah, how I'm gonna structure the information so I can use the library later. Or maybe there isn't libraries actually for Rust to read. I know that there is the CSV library, but optimized libraries for reading in CSV and manipulating, like you can use NumPy and pandas in Python to do special things, or pandas specifically, or even polars where you can group stuff and apply functions and it's faster. So that's what I'm thinking about. Because obviously I think I can, given that I can write the file with strings, I can format in a way that I get the data frame at the end, but then the question is, can I use any library to perform from operations in columns in the same way that I do in Python at the end to make the analysis? Oh, but I guess the other thing that I can do is after I have, yeah, but then it doesn't make sense. That's the other thing that I've been thinking about, how to integrate Rust with Python, because the Python side is better for machine learning because you have a lot of libraries. So ideally, I want to deal with all of the data in Rust because it's faster, and then connect that with Python to the machine learning. Which in this case, probably not going to do because I'm going to integrate this with PySolver, so maybe it's not necessary. But in the future, I think that's what I'm going to do eventually. I think I'm going to read this so I can close. Yeah, usually I open a bunch of different tabs and then I go closing the ones that are, so for videos, the smaller video, the shorter video I watch first and then I close. So I open everything that is related to what I'm trying to do, then I try to close them as fast as possible.
Difference between CSV and Excel. CSV refers to comma-separated values. It holds plain text as a series of values, cells, separated by commas, in a series of lines, rows. CSV file can actually open in a text editor and read it. There are lots of applications for reading CSV files, and many languages provide built-in functions that simplify reading/writing CSV format. These files are majority used by professionals in data analysis or visualizations. Excel. Microsoft Excel is used to display the data in horizontal and vertical rows. The data are usually stored in the cells. We have an option of formulas in Excel that can be used for data in its place of storage. You can even add any charts, graphics, etc. to make it more presentable. Below is a table of differences between CSV file and Excel file. sr.knox-vexel1 CSV stands for comma-separated value.ms. Excel stands for Microsoft Excel. Point 2, it is a plain text format with a series of values separated by commas. It is a binary file that holds information about all the worksheets in a workbook. Point 3, CSV can be opened with any text editor in Windows like Notepad, MS Excel, Microsoft Works 9. etc. Excel file can be opened with Microsoft Excel doc only. Point 4, it is a standard of saving tabular information into a delimited text file. It is a spreadsheet application that saves files into its own format. Point 5, CSV file saved with extension as .csv. Excel file saved with extension as .xls/.xlsx. Point 6, it consumes less memory than Excel. It consumes more memory than CSV. Point 7, no such feature is available in CSV format when it is compared with Excel. It also provides the user option for external linking of data from other sources, and also the user can do custom add-ins. Point 8, it is not easier for the end user to read large files in CSV. It is easier for the end user to read large files. We use cookies to ensure you have the best
Yeah, I thought this was the difference between CSV and HF.
Q. Compare archive. A. Advantages and disadvantages of archiving text in HDF5 data formats. HDF5 is a data storage format that can store a variety of data types and is designed for flexible and efficient I/O and for high volume and complex data. HDF5 is a standard format that is portable and self-describing. HDF5 stores data in binary format native to a computing platform but portable across platforms. The binary format native to computers makes the format the more efficient for computers than text formats, example.txt or .csv, that is meant for humans to read. Text file formats use ASCII data that is portable across different types of computing platforms but use more space to store numeric or Boolean data. In addition, computers require significant processing to convert their natural numeric and binary data into unnatural ASCII data formats. For high-performance or real-time systems, this extra processing may be unavailable to too costly. Related information. Presentation video, published in August 18, 2020. 4 minutes read. Working with HDF5 files and creating CSV files. HDF5 to CSV conversion. Photo by Mr. Cup/Fabian Barrel on Unsplash. In my last article, I discussed the steps to download NASA data from guest disk. The data files downloaded are in the HDF5 format.
Good morning, everyone. Thank you
So guys, we'll start with this one.
Channel on YouTube, and this is one of the videos as part of our tips and tricks series. And as you may have noticed, these videos are released on Mondays, and typically I answer your questions if I see a trend in your questions as part of these series. So keep an eye on these ones on Mondays, and in addition, I schedule my regular videos for Wednesdays, as you probably know. If you are not a subscriber, please go ahead and hit the subscribe button right now. In this video, I'm going to talk about understanding the Keras train model. Like, you train your model and then you save it. What information gets saved, and can you actually have a look at how the structure of the saved model looks like by opening a HDF file using a viewer. So if this is of your interest, let's go ahead and continue this video. If not, I really recommend continuing this video because you may learn something new from this, especially if you're using Keras. If you're using some other framework, I'm not sure how much useful this video is going to be because the structure of the saved model is probably different depending upon your framework. So this is definitely appropriate for the ones who are working with Keras. So let's jump in. So we can clearly follow a path, follow a structure. I'm going to use an example from video 228. This is where we trained a UNet for aerial imagery segmentation. Again, it doesn't matter. You can load any HDF5 file, whether it is classification or semantic segmentation. The process that I'm going to show you is going to be pretty much the similar. So this is more of a understanding type of video rather than just going through line by line of the code. So I'm just mentioning this in case you're a regular viewer of my channel, you know exactly what file I'm talking about. So we trained a model using a simple UNet, and as you can see, my UNet has a convolution block with 2 convolution layers and dropout and max pooling, const max pooling, and then we're going from 16 to 32 filters to 64, 128, 256, and then back to 128, 64, and so on. This is a classic UNet, and as part of your expansive path or decoder path, we are going to do some concatenation operations. And as you probably know, our con layers and con2d transpose layers are trainable. They have trainable parameters, but the dropout and max pooling, of course, they do not have trainable parameters. All of that hopefully will make sense once we print out the model summary and also once we open the saved HDF5 file. So we use this to train a model. So and I save that model as HDF5 file or H5 extension, it doesn't matter. We save the model using model.save in Keras. Now, a few months later, I'm back and looking at this. I'm like, what information can I get out of it? And can I go ahead and load this model and do other tasks? So in order to do that, let's go ahead and write a few lines of code here, which I did. So because we have used Keras, I'm going to use principal import Keras. And in fact, let's go back and see how we imported Keras right there. So here I did this was from a few months ago, and I directly imported Keras.models, and now I'm using from TensorFlow import Keras. And something different. This is the new way I taught myself to be a bit more organized. Just get everything from TensorFlow. Okay, so from TensorFlow, let's import Keras, and you probably know that to load a model, we have to we can just do Keras.models.load model, and this is the model that I'm trying to load, right? This is the one that I saved on 7th May 2021. So let's go ahead and try to load this model. I said try because it's going to throw an error, as you probably some of you know. The reason it is throwing an error is because it doesn't know what this dice loss plus 5 focal loss is. What is that? Well, it's throwing an error because in the model that it stored from 7th May 2021, it has some information about dice loss plus 5 focal loss. In fact, this was the last function I used while training the model. So it's saying, hey, I don't know what this is. Give me that information. So obviously that information did not get stored in its entirety as part of the models because it's not going to store that specific function that I defined. So you need to have access to that. And that function that I defined back in the day, a few months ago, was I hope I can find it right here. Yeah. So this is the function. So I'm using dice loss, focal loss, and I combined dice loss and focal loss with a multiplication factor of 5. That's exactly why I said 5 focal loss. But you need to know this. You cannot open someone else's H5 model file and automatically expect to understand exactly what in the world this is. So it makes sense if you appropriately label your functions right there. So let's try this one more time. So here I am importing my dice loss, my focal loss, and I am adding my dice loss and focal loss with a weighted average of weight of 5 to my focal loss. And I define this as my total loss. So let's go ahead and by the way, I'm importing the dice and focal loss from a library called segmentation models, but that's immaterial. Whatever function you use in the past, go ahead and do that, right? So let's go ahead and import this. So now I know that my total loss is what it means when it says dice loss plus 5 focal loss. So I'm going to copy that parameter. And as you probably know, when you load models, any custom object that you define, you can actually define that as a dictionary right here. When you load the model, so I'm defining my dice loss plus 5 focal loss is nothing but my total loss. Yeah, that's the total loss. So let's go ahead and run this model. When you do that, it should fail again because I have another custom object called Jacquard coefficient because that's the one that I have used as part of my, no, where is it? Yeah, as part of my metrics right there. because we are compiling the model with optimizer information, with loss information, and with metrics information. So it needs to have all the information about these three. It knows what atom is because that is coming from keras. I'm not writing a custom function. If you have written a custom optimizer, then you need to provide that too as part of your custom objects. So again, we're trying to unravel what's stored as part of the same model. Of course, loss is saved and also the metrics. So it's saying, I don't know what you mean by Jacquard loss, so tell me what it is. So that's exactly what I'm trying to do. So from this model that we just defined, in fact, there's a function called Jacquard coefficient that I defined as part of this Python file. Let's go ahead and import that. Go ahead and import Jacquard coefficient. And now as part of my custom objects, in addition to dice loss specify focal loss, I'm defining Jacquard coefficient as this. So now this should hopefully work without an issue. And now we loaded our model successfully. So we loaded the model in its entirety. So let's go ahead and print out the summary. And if you look at the summary, this has all the information right there, right here, the layer name, how many filters, and how many triangle parameters, all the information is printed. Because we are using this API for model.summary to actually print this out. So basically, it's extracting the summary information from the loaded model. That means our model, the HTF5 file, had this information or still has this information stored in it. We'll again open this HTF5 in a minute and then just see exactly how the information is stored. Now, because this is stored, we can also, we're actually bringing, looking at the model and we are extracting relevant information. So if you want the layer names, right, and here the layer names are exactly what this means. But I just want to actually store a lot of information in a very hierarchical way. So you can see there is a group, and within that group you can have another group, and then metadata and so on. As soon as we open HTF5, a lot of information in a very neon signs are and they put together some documentation that I have in line about HTF5. So it's a container format.
Neon signs. Interesting. Yeah, this one is gonna be useful, I think.
If you just want to simple answer, it's a container format that actually stores a lot of information in a very hierarchical way. So you can see there is a group, and within that group you can have another group, and then metadata and so on. As soon as you open an HTF5 file, you'll realize exactly what this means. But I just want to give you a quick overview of what that is. And to open the HTF5 file, go ahead and download, go to hdfgroup.org or just Google search for HDF viewer or HDF view. And download it. You need to register with an email, but once you do that, go ahead and download it for your operating system. I downloaded the Windows 10 version right there, installed it, and now let's go ahead and open it. And this looks like a bit of an older Windows 95 or 97-ish look, but that's okay. That's exactly what we wanted to do. So let me open the HTF5 file that we just looked at. So that was this file, 7th May 2021. Let's go ahead and open it. So let's start from here. First thing first, if you click on, you can open multiple HTF5 files right here and then navigate to them. But let's focus on only one for now. Let me click on the title right there on the main link of the hierarchy. As you can see, it starts right there. Within that, you have two subdirectories, if you want to call that. Again, this is a container, and if I go back, those two are, think of these as just these groups. And in each group, you have some metadata associated with that. So let's get back right here. So you have model weights and optimizer weights. These are the two groups that you have here. Right away, I would say maybe you can ignore optimizer weights. Actually, let's start the topic for a second. Let's go ahead and click on this and see what information is here. First of all, it stores the information about your backend. I believe that means is it TensorFlow or not? Yeah, there you go. So it says okay, you're using TensorFlow backend, and when it comes to keras, what keras version are we using? 2.4. So the model here got trained on keras 2.4. So it does have information about your keras version and model configuration. This is important. So what is the configuration of your model? Let me bring this to the middle, and when you double click and open, stop to see anything. Let's go full screen. There's a lot of information here. This is basically the model structure. You see the class name unfade, yeah? And when we did model.layers, this is what it's looking for. Layers is a dictionary right there. You see model.layers. Within model.layers, we are looking at layer.name. So if you go all the way and look at layer.name, you see how it says input 1 right there. So the first name it looked at was input 1. If we go back to our code, that should be the first name right there. And then it looks for the name tag again, and then it'll of the model. Right, this is the structure. So if you import it without any weights or anything, then this gives you the structure. Then you're good. But you want the weights. When you're doing transfer learning, you want to load the weights. And how are the weights stored? There are two things that you'll see here: model weights and optimizer weights. And I would say if you just want to use your model summary, so let's go back. But how many weights do you have? You have 3 by 3 times 64. That many weights. So if we go back and
I'm gonna search for this to see how it is recommended to write to Rust. To write to Rust.
Introduction. This book is an introduction to the Polars data frame library. Its goal is to introduce you to Polars by going through examples and comparing it to other solutions. Some design choices are introduced here. The guide will also introduce you to optimal usage of Polars. Even though Polars is completely written in Rust, no runtime overhead, and uses Arrow, the native Arrow 2 Rust implementation as its foundation, the examples presented in this guide will be mostly using its higher-level language bindings. Higher-level bindings only serve as a thin wrapper for functionality implemented in the core library. For pandas users, our Python package will offer the easiest way to get started with Polars. Goals and non-goals. The goal of Polars is to provide a lightning-fast data frame library that utilizes all available cores on your machine. Unlike tools such as Dask, which tries to parallelize existing single-threaded libraries like NumPy and Pandas, Polars is written from the ground up, designed for parallelization of queries on data frames. Polars goes to great lengths to Reduce redundant copies. Traverse memory cache efficiently. Minimize contention in parallelism. Polars is lazy and semi-lazy. It allows you to do most of your work eagerly, similar to pandas, but it also provides a powerful expression syntax that will be optimized and executed on within the query engine. In lazy polars we are able to do query optimization on the entire query, further improving performance and memory pressure. Polars keeps track of your query in a logical plan. This plan is optimized and reordered before running it. When a result is requested, Polars distributes the available work to different executors that use the algorithms available in the Eager API to produce a result. Because the whole query context is known to the optimizer and executors of the logical plan, processes dependent on separate data sources can be parallelized on the fly. Performance rocket. Polars is very fast, and in fact is one of the best performing solutions available. See the results in H2OAI's DB benchmark. The image below shows the biggest datasets yielding a result. Polars TPCH benchmark results are now available on the official website. Current status. Below a concise list of the features allowing Polars to meet its goals. Copy on write. Free clones. Cheap appends. Appending without clones. No block manager, i.e. predictable performance. NaN are different from missing. Bitmask optimizations. Efficient algorithms. Its CSV and Parquet readers are among the fastest in existence. Query optimizations. Filtering at skin level. Projection at skin level. Aggregations at skin level. Simplify expressions. Parallel execution of physical plan. Different group B strategies based on data cardinality. SIMD vectorization. NumPy universal functions. Acknowledgements. Development of Polars is proudly powered by
And this is the introduction.
Getting started. Installation.
Oh, fuck. I'm gonna stop this. What? Red ballers. I made a typo there.
Oh, but I was but I was wrong. And in general, I started this as a 2D dataset, but as I said, we need to slice our cube in 3 dimensions. I started the topic as a 2D dataset, and I was thinking that I need to make another instance of this dataset transpose, and just I could have 2 datasets with the same data, but one is the original data and another is transpose version. And cat is the first.
Apparently there is a module called
cat with
this.
spirals and to achieve the greatest performance.
If I can stop this.
No, I was going to ask, like, you're not just reading a contiguous region from the data set, right? You need to have like at least the rows to be like random.
Ballers.
Is that right?
I think this is the most this is the hardest way when we choose arbitrary rows. Usually we have to choose either contiguous array from 2D dataset. Contiguous array, I think from first to 5,000 rows is a contiguous array, or each 5,000th row, or probably 5,000 arbitrary rows. And the last case when we got our 2D dataset by column, we need to retrieve probably one column at some position. This is my problem.
Yeah. So I saw your post on the HDS forum, and I was curious to try it out. And I kind of restricted myself to this 2D case in the first attempt, just because that was a little bit easier to think about. So let me show you what I've done so far, and then you can tell me how cool this is to your case, right? So first of all, there is I created this test file.
Yeah, I don't know the kind of for first time.
Yeah.
Okay, let's have a look at this.
So here's what it does. You guys see my screen, and let me see if I can share this on the chat. I'm not sure how to chat is. Okay, I know. It's in the HS group GitHub HTTPS test perf read 2D file. And what it does is it takes a file path and then has these options for bucket h5 path, which apply bucket is for HTTPS, h5 path is where the dataset is, x length and y length for how many rows and columns to return, stride is stride factor, and iter is iteration count, how many times repeat the test. And so it goes through. And
The thing that I'm unsure about is if in Rust you're supposed to do a hash map and then a list, because in Python you do an object and then you make key value pairs and then you create lists and they have to be all of the same length, and then that's how you create the data frame. And I guess that's the format that you can think of in Python. It's just dictionaries with a bunch of lists. But then in Rust, I'm not sure if I should do a hash map and then put vectors into the hash map. Yeah, like string slices mapped to vectors with a hash map, and then append that to the H5.
These options, and then does first a simple hyperslab selection. So we're just doing this data set, I1, I2, J1, J2. So we're turning that X length by Y length block of data. And the second case, we have stride factor. So here, the axis is data set start to end described, and then a contiguous number of columns along the second dimension. And in the third case, we first computed a set of random indices. Right, so everything is random here, like this random.rand to get the starting index. And I wanted that, so we're not inadvertently advantage of data that was recently cached by the axis. So here, to create indices, we create a list and we randomly choose indices along it. And if I'm lucky enough not choose one that was not chosen, I add my list. And then we, again, with a random j to the second index, and we do data set indices, comma, j to y length. And then we just print time. So if we run this, so here,
So it does work with CSVs.
So I have, I'm running this on this terminal connected to an EC2 instance, which has a rotating drive in slash data. And I look there is,
Oh. I guess I can look into my other project because the learn Italian thing, I appended to a CSV. So if I do it with a CSV on this one, I can append, I can use the same thing. But then I'm using a different library, but then I can use polars on this one. It looks like it works with CSV. I'm just not sure if it works with H5.
To its file C_2D-5, it is about 100 gigabytes. And if anyone asks,
but I can probably structure the same way for H5 as I did with CSV. And then I can test if it's going to work with polars or not. And then I can see the trade-offs of using CSV and using polars or using H5 and not using polars.
For bounds of size, or would your data sets possibly get larger and larger over time?
Yes, it can be get larger. There's two types of data maybe. The first type is a cube, can be represented as a cube. Note it has a regular spacing along each axis. And these types of files, now they can be 100 gigabytes and maybe more, but usually they have about 10 gigabytes, 20 gigabytes of size. But 100 gigabytes, it's a usual for nowadays.
And so I was going to say, why requirement for a rotating drive versus SSD drive?
Why we can use SSD? Just to make a little bit clear, companies that are probably will have a cluster, they tell that this is expensive.
Right.
And they can afford it. They use
Yeah, but I mean, a few hundred gigabytes is not super expensive for a drive nowadays. And I wrote a blog a few weeks back comparing the performance of rotating drives versus SSD for a similar kind of test case. And the SSD was way faster, like more than a factor 10 faster. So that's something to think about. But anyway, so I set this up on a rotating drive just like you had. And if we do h5ls-b/data/c2d, we see it's a data set 25 million by 1,000 columns. And I set the chunk shape to be 524 by 1,000. So that since the second dimension is a relatively small extent, and since frequently we want to access the entire set of rows, this makes sense, right, to have a chunk shape where the second extent was the chunk layout was the data set layout. And in HSDS at least, we want the chunk size to be around 2 megabytes. So that's how I get 524 for the first dimension of the chunk layout. Okay, so now let's run our test case. So I'll just run it with the so Python read to data and slash data here, and I'll set the stride to be 1,000. I think the default is like 5 or something. So first records this contiguous selection, and as you can expect, that's relatively fast. Since we're getting 1,000 rows, we're only accessing 3 or 4 chunks in this case. So about 8 megabytes of data on disk. And then we do the stride selection. Now we're accessing 1,000 chunks, right? So we'll need to read 2 gigabytes of data from disk to get this result. And that took 22 seconds, 23 seconds almost. And now one of the random indices. So here we're doing selection where it's indices 5822, 14738, blah, 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 this out. So Kubernetes deployments are called pods, and we have 50 HSDS pods running currently. There's a parameter -s length, the stride selection. That's likely to have the AWS console. So in HSDS lab, normally scale the pods to be, say, 4. So let's go. It should be, you see we have a bunch of containers called HSDS DN _914.1. All network traffic of one core program. So either HSDS files or HSDS.
Yeah, not very interesting for me. I'm just gonna close this. This one should be really interesting. I think I watched these videos, and then after that I read the documentation and write through or try to read or write with the polars, the HF, and then if I can read from the file, then I'm gonna see if I can structure the file in a way that I can append to it in the same way that I would do with append as data frame in Python. After I do that, then I will start thinking about I think I'm gonna have to use regex patterns, even though I don't want to, because I hate using regex. It's very difficult for me. but I'm probably gonna have to end up using that because I'm not gonna be able to filter with the string slice, I think. So the plan is to filter through the file, the h5 file with the text and the poker, and then find the patterns. And I'm probably gonna have to use regex to find each pattern and then append to a vector or something like that, and then write to the CSV. Or to the HF. I'm probably gonna have multiple HFs for different patterns, I guess. And then after that, only after that I'm gonna study to see if it's even possible to connect this to PySolver. Probably it is, but I think there are some limitations because the only thing that I can connect to is by creating the scripts, and because in PySolver you can create a bunch of scripts and programmatically determine for the solver to run all of them sequentially. So I think I will be able to do that, but then the analysis part is the thing that I'm not sure of. Because obviously I don't want to do the analysis manually. I want to compare the probabilities of the solver with the thing that I built. But in case I can't do that, I'm thinking about going to their Discord and talking to the devs that build this and seeing if they can make it happen. I'm gonna tell them to watch the stuff that I did and see if they can make this happen, because it's probably gonna be good for them if they would create this, because it makes sense. You're just comparing your data with the solver and then seeing the differences in statistics, which allows you to learn much faster than going solve by solve, because I can see the probabilities and then I'm gonna have a rough understanding of how I'm deviating from what strategy I should be implementing against my opponents, and in which nodes of the tree I should be doing that.
All right, let's do this. How are you, data scientists and engineers? How are you, business people? What's up, nerds? Did you grab that?
And then eventually I can probably program something that automatically downloads my hand histories. Maybe not, because to interact with the sites, poker sites, I can't do it. But maybe, yeah, I probably can create something that after the download, it directly updates into the stuff that I'm building, and then calculates the differences in the probabilities connecting with the PySolver.
We're starting. This is Data Science at Home, the podcast about machine learning, artificial intelligence, and more good stuff. I am Francesco. I'll be your host for the next 30 minutes, so grab a cup of coffee and join me as we learn more about the topics we love most. Welcome back to another episode of Data Science at Home podcast. I'm Francesco, your host. Today's going to be quite interesting, actually very interesting. It's one of the rare moments in which I have in front of me the author of the library that I've been personally using in the last month, a few months, and I'm speaking about a very important crate. A crate is equivalent of package in the Rust jargon. I'm with the author of Polars. Welcome to Richie Vink. Hi, Richie, how are you doing?
Yes, hi. Yeah, I'm doing fine. Thank you. Thanks for having me.
Yeah, so I'm very glad to have you here on the show. I'm pretty sure that the followers of this episode and of the podcast in general will definitely love to hear more about what Polars is and what you've been working on so far. So do you mind introducing yourself to the followers of Data Science at Home podcast?
Yeah, hi. Well, my name is Richie Vink. I'm just a guy who has background in data science, machine learning. I like to implement algorithms from scratch and blog about them. And I did this quite often.
It looks like this is a podcast, so it might be better to listen to this while I play poker. I think I'm going to read these things here while I'm streaming.
Hierarchical data
And
formats.
maybe watch the other videos as well. I think I'll be right back. We'll go to the bathroom.
Hierarchical data formats. What is HDF5? Learning objectives. After completing this tutorial, you will be able to explain what the hierarchical data format, HDF5, is. Describe the key benefits of the HDF5 format, particularly related to big data. Describe both the types of data that can be stored in HDF5 and how it can be stored/structured. About hierarchical data formats, HDF5. The hierarchical data format version 5, HDF5, is an open source file format that supports large, complex, heterogeneous data. HDF5 uses a file directory-like structure that allows you to organize data within the file in many different structured ways, as you might do with files on your computer. The HDF5 format also allows for embedding of metadata, making it self-describing. Data tip asterisk HDF5 is one hierarchical data format that builds upon both HDF4 and NetCDF, two other hierarchical data formats. Read more about HDF5 here. The HDF5 group. Hierarchical structure, a file Hierarchical structure, a file directory within a file. The HDF5 format can be thought of as a file system contained and described within one single file. Think about the files and folders stored on your computer. You might have a data directory with some temperature data for multiple field sites. These temperature data are collected every minute and summarized on an hourly, daily, and weekly basis. Within one HDF5 file, you can store a similar set of data organized in the same way that you might organize files and folders on your computer. However, in a HDF5 file, what we call directories or folders on our computers are called groups, and what we call files on our computer are called datasets. Two important HDF5 terms. Group, a folder-like element within an HDF5 file that might contain other groups or datasets within it. Dataset, the actual data contained within the HDF5 file. Datasets are often, but don't have to be, stored within groups in the file. An HDF5 file containing datasets might be structured like this. HDF5 is a self-describing format. HDF5 format is self-describing. This means that each file, group, and dataset can have associated metadata that describes exactly what the data are. Following the example above, we can embed information about each site to the file, such as the full name and XY location of the site, description of the site, any documentation of interest. Similarly, we might add information about how the data in the dataset were collected, such as descriptions of the sensor used to collect the temperature data. We can also attach information to each dataset within the site group about how the averaging was performed and over what time period data are available. One key benefit of having metadata that are attached to each file, group, and dataset is that this facilitates automation without the need for a separate and additional metadata document. Using a programming language like R or Python, we can grab information from the metadata that are already associated with the dataset and which we might need to process the dataset. Compressed and efficient subsetting. The HDF5 format is a compressed format. The size of all data contained within HDF5 is optimized, which makes the overall file size smaller. Even when compressed, however, HDF5 files often contain big data and can thus still be quite large. A powerful attribute of HDF5 is data slicing, by which a particular subsets of a dataset can be extracted for processing. This means that the entire dataset doesn't have to be read into memory, RAM, very helpful in allowing us to more efficiently work with very large, gigabytes or more, datasets. Heterogeneous data storage. HDF5 files can store many different types of data within the same file. For example, one group may contain a set of datasets to contain integer, numeric, and text, string, data. Or, one dataset can contain heterogeneous data types, example both text and numeric data in one dataset. This means that HDF5 can store any of the following, and more, in one file. Temperature, precipitation, and PAR, photosynthetic active radiation, data for a site or for many sites. A set of images that cover one or more areas, each image can have specific spatial information associated with it, all in the same file. A multi- or hyperspectral spatial dataset that contains hundreds of bands. Field data for several sites characterizing insects, mammals, vegetation, and climate. A set of images that cover one or more areas, each image can have unique spatial information associated with it. And much more. Open format. The HDF5 format is open and free to use. The supporting libraries, and a free viewer, can be downloaded from the HDF group website. As such, HDF5 is widely supported in a host of programs, including open-source programming languages like R and Python, and commercial programming tools like MATLAB and IDL. Spatial data that are stored in HDF5 format can be used in GIS and imaging programs including QGIS, ArcGIS, and ENVI. Summary points, benefits of HDF5. Self-describing. The datasets within HDF5 file are self-describing. This allows us to efficiently extract metadata without needing an additional metadata document. Support a heterogeneous data. Different types of datasets can be contained within one HDF5 file. Supports large, complex data. HDF5 is a compressed format that is designed to support large, heterogeneous, and complex datasets. Supports data slicing. Data slicing, or extracting portions of the dataset as needed for analysis, means large files don't need to be completely read into the computer's memory or RAM. Open format, wide support in the many tools. Because the HDF5 format is open, it is supported by a host of programming languages and tools, including open source languages like R and Python and OpenGIS tools like QGIS.
Oh, nice. So there's a bunch of different tutorials. I think I'm gonna read all of this stuff. and read the Rust simultaneously. Not at the same time, obviously, but one and then the other. Yeah, probably it's gonna be better to use H5 than CSV. And it probably works with polars because, as I understand now, it's it's kind of like a superset of CSV or of a pandas data frame where you can have a bunch of different data sets on the same file structure. So I assume that it must work with polars as well, if polars works with CSV in Rust. Yeah, maybe it's better to read this whole thing than to read each tutorial, or maybe I'll read both as well. Let's see how long this. I hate when this thing does that. It doesn't work because of the format, probably. Just adding the file so I can read. Okay.
June 2019.
I wish they had a faster speed, but I searched for other text-to-speech things, and all of them sucked. I think this is the best one I've found. But the thing that it sucks is that they only go up to 540, which is really slow with the voice of this guy. Okay, so this is a very big thing, so it's gonna take 4 hours to read everything. So I think I'll read the articles first, and then maybe I'll read this later.
June 2019.
Some other time.
HDF5 Users Guide, page 1.
I want to make sure that I understand what's going on.
1. The HDF5 data model and file structure. 1.1 Introduction.
This one I can close, I think. This one's the one that I just opened. Close this. Yeah, I don't think I will read. I don't have enough time to read all of this stuff, so. Or maybe this one is useful. Yeah, maybe eventually I'll read all of them, but. I think I'll start with these ones. But I'm gonna watch these videos first. Or maybe I should. I think I should go. I'm gonna.
Installation.
I'm gonna go through this first, and then try to write things in Rust. Oh, but it looks like this is in Python. And I'm pretty sure I opened the Rust documentation.
Rust.
Okay.
df.lazy.filter, plcol,
So this has the Rust version. Okay, so the
Rust.
Rust
Import
version is
polars as
here.
plprint, plreads, https://j.mp/irisks.lazy.filter, plc. This example is presented in Python only, as the eager API is not the preferred model in Rust. Import polars as pldf equals plreads, https://j.mp/irisks, print, df.filter, plcol, cpl-length, 5.groupb, species.ag, plall.sum. The snippet above will output shape 3, 5, species cpl-length sum cpl-width sum petal-length sum petal-width sum dash dash dash. Dash dash strf64 f64 f64 f64. As we can see, polars pretty prints the output object, including the column name and data type as headers. Lazy quick start. If we want to run this query in lazy polars, we'd write Python Rust import polars as plprint, plreads, https://j.mp/irisks.lazy.filter, plcol, cpl-length, 5.groupb, species.ag, plll.sum.collect. When the data is stored locally, we can also use skinksv in Python or lazy CSV reader in Rust.
Yeah, but it's using CSV reader.
When the data is stored locally, we can also use skinksv in Python or.
But I guess it comes from Rust. Just gonna copy this and put on my thing here. Then obviously I'm gonna remove this because, or maybe I should just, yeah, I'm not gonna remove actually. I'm just gonna change the methods here. Oh, maybe not, because I can open the CSV based on the, yeah, so I'm gonna remove this. Based on the name. Oh, actually, I don't remember now if I should put the file path there. So I guess that should be. And I also need to make this public. And then puts here. Actually. I should probably create another file folder as well. But then the only thing that I'm not sure is if I should make it like this. And this is not gonna use this. Also not gonna use this, but it's useful to leave it here because I might use it. I'm probably gonna use it in the future actually. Yeah, maybe. Yeah, I'll have to think about this, but there are multiple different ways that I can split things. I can choose to create complex regex to filter the file first and then create the data frames based on that, but I don't think that's what I'm gonna do. I think it's gonna be better to make it as simple as possible to filter the text and then create a bunch of different H5 files and then filter the files or manipulate the files to get the thing that I want. So pretty much try to be as basic as possible when filtering the H5, the first H5, and then that has all the hands, and then increasing complexity when I have the data frames. I don't know what this does, so but I think I'm gonna run this and see what happens.
When the data is stored locally, we can also use skinksv in Python, or lazy CSV reader in Rust to run the query in lazy polars. References. If you want to dive right into the Python API docs, check the reference docs. Alternatively, the Rust API docs are available on docs.rs. Lazy API. The lazy API builds a query plan. Nothing is executed until you explicitly ask polars to execute the query, via lazyframe.collect, or lazyframe.fetch. This provides polars with the entire context of the query, allowing optimizations, and choosing the fastest algorithm given that context. Going from eager to lazy is often as simple as starting your query with .lazy, and ending with .collect. So the eager snippet above would become Python, Rust, df.lazy, .filter, plcol, cpl-length, 5, .groupb, species, .ag, pll, .sum, .collect.
So I guess it has to be coming from the CSV reader has to be coming from this thing here, given the example. The only thing that makes sense. The other is the request. This thing I don't know what it is, but I assume that is for the type here. And it looks like there's something wrong with this. And so I'm supposed to wrap this. Where is this? Lib. Wrap this with this. I'm not sure if I should do the same thing here. Or I actually I can probably do all of them in one thing. So do them like this, probably. Let's see if this works. Hmm. Oh, so I should remove this on here. Probably gonna get another error. Okay, so like this. Hmm. Oh, I need to get the function of each one. Maybe that's the thing. Or should I put use here? Hmm. Oh, I guess they did the wrong way. Should put the file name there. I only have one file. That's the difference. Okay, so here, this file. Oh, it's files, not file. As I can remove this. Hmm. It's probably wrong, the solution. Yeah, I remember reading this and it was confusing. And I tried to do it this way and then it didn't work. The thing is, it was working the way that I did before. Maybe I should go back all the way. But the difference is that I had the files in the same directory. That was the thing. It looks like the 2 hours are done, so I think I'm gonna stop here. There's a lot of stuff that I have to do off streaming and study and stuff like that. It'll probably take me a lot of time to stream again, but I think I'm probably gonna watch these videos off stream, all of them, and then read some of this stuff off stream as well, if I have time, because I have the other stuff to do. But then next time I'm gonna continue to do this poker project and study the H5 format and how to optimize the data frames with pandas, and then continue to work on the poker tool. I'm probably train PyCharm as well, or VS Code. So see you then.